Our plan at this point is to deepen our understanding of how to calculate probabilities associated with a binomial experiment. You'll recall, to begin, that anytime we define a binomial random variable, say a binomial random variable x, this x represents the count of successes in n independent trials. And our n represents the number of trials in the binomial experiment, whereas p represents the probability of success in one independent trial. Now, having defined these parameters, n and p of the binomial distribution, we might ask, where are they coming from? So, if you recall earlier, for every binomial experiment, we can define these two key characteristic features of the binomial experiment. N, the number of trials, the fixed number of trials, and P, the probability of success from one trial to another. We did that in this case too, where we had P equals 0.20 and N equals 5. So these are characteristic features of the binomial distribution. So anytime we adjudge a scenario or an experiment to follow a binomial, the patterns of a binomial experiment, we can identify them by describing the parameters. Now, when we want to compute any probability associated with a binomial experiment, we use this formula. Eventually, you would not need to remember this formula because we will use technology in order to help us compute or get the values that this formula can help us get. But in particular, do not forget, n is the number of independent trials, p is the probability of success, and x is the count of successes in n independent trials. It is bounded above by n, that is, the number of successes in n trials can go from at least 0 to at most the number of trials. To illustrate this, let's take the first example, where we're going to use the binomial distribution to describe each situation and find the required probability. So, we take the first question here. Suppose 80% of trees in a forest of 300 trees are infected with a virus, and we take a simple random sample of 5 trees to test for the virus. Right here at this point in time, I can already spot how many trees I'm going to test. That will be my sample size. So it means that my n is equal to 5. And in general, what is the probability that a tree will be infected with a virus in general from previous data evidence? It is 80% or 0.80. Now, this tells me immediately that x, the number of trees that have the virus, definitely follows the binomial distribution with n equals 5 and p equals 0.80. With that said, I am ready to focus down on the question. What is the probability that exactly 2 of the 5 viruses have the virus? So, probability that x, the number of trees that have the virus, is exactly equal to 2. That is what this question wants us to find. This is a probability tied to a binomial experiment. Since that is so, I can use this formula where you have, so I'm going to write that formula here, n combination x. I can write it this way too, multiplied by p raised by x multiplied by 1 minus p raised by n minus x. So the next step is I am going to replace n with p, or sorry, n with 5 and p with 0.80. So let's do that. So my n is 5 combination x, x is 2, p is 0.80. So p is 0.8, excuse me, p is 0.80. So we have 0.80 there, raised to power 2. And then 1 minus 0.80, which is, of course, 0.20. So I'm going to replace that with 0.20. N again is 5 minus x again is 2. So how do we compute this? In order to get 5 combination 2, take note, this represents in how many ways can I pick 2 distinct objects out of 5 different objects. I can use StatCrunch to help me out with this. So, to use StatCrunch, I will go to Data, then go to Compute an expression. I will type COMB. This is a command to StatCrunch to help me compute the combination 5, 2. Close the parentheses and hit compute. So 5 combination 2 is equal to 10. So I have the value I need here. So it means that my 5 combination 2, when computed, this is equal to 10 multiplied by 0.80 raised to power 2 and 0.20 raised to power 3. This will give me on my calculator the value 0.0512. Well, could we have used StatCrunch to help us with this same probability? Yes, we could have. So let's go back to StatCrunch here. All right, I'm going to close this and have this. Okay, so back in StatCrunch, I could have gone to my stat, calculators, binomial. This we did earlier. Go to binomial, set up the right parameters here. N is equal to 5. And the probability of success here is 0.80, as we see from the question. N is 5 and P is 0.8. And I want the probability of x equals to 2. So going back here, I want the probability of x. I'm going to choose equals 2 and hit compute. And the amount of probability, the probability mass at the point x equal to 2 is 0.0512. So you see that both the calculator in StatCrunch, and the formula give exactly the same value. Just to emphasize this fact, let's again use technology and the parameter values n equals 6 and p equals 0.8 to compute the probability values for the probability mass function given here. So in this case, we're going to set up our n equals 6 and p equals 0.8. So I'm going to do that. N equals 6 and p is what, 0.8. And I'm just going to pick a random value here. So let me start out with 0. And I have this, which is 0.00064. Please be careful when working with the number of zeros. Count closely. So the answer for x equals 0, which is this, I have taken it to my working board. All I need to do is to adjust the StatCrunch calculator so that my x is now equal to 1. So I can do that. I can go in here, change this to 1, hit the enter, and I have the amount of probability at 1 here, which is 0.001536. That is right here. And I can keep the process going on. So for x equals 2, I'll do the same. Let me do that 1, 2. Going back here, I have 2 and equal to this 0.01536, which I have there. So you can continue the process and you will get all of these values. Remember, this table represents a probability distribution model. The sum of all of these probabilities must be equal to, as you rightly said, 1. And each of the probabilities is a number between 0 and 1. In this way, it ties with what we established earlier, as far as any probability model is concerned. Then, with that said, let's go into an applied problem. We are told here that according to an airline, flights on a certain route are on time 80% of the time. Suppose 17 flights are randomly selected, and out of those 17 flights, the number of on-time flights is recorded. Let X be the number of on-time flights. We would like to explain why this is a binomial experiment. To answer this question, we ask, what is the trial here? The trial is each flight. And does each trial lead to two possible outcomes? Yes, the flight is either on time or not on time. So that's the first thing. Each trial leads to two possible outcomes. The next condition or observation is that we are trying exactly 17 flights. So we have n, the number of flights or the number of trials. The number of trials is fixed. It is fixed. We're only trying 17. Then, do we have independent trials? Well, that a particular flight is not on time does not dictate that the next flight will also not be on time or would be late. So in this case, you also have independent trials. And then last but not the least, the probability that a particular flight will be on time is 80%. P equals 0.80. And this is true for each and every flight based on historical evidence. So in this sense, since all these conditions are met, this is a binomial experiment. Question B, what is the probability distribution of X? X, in this case, definitely has the binomial distribution with n equals 17, and the probability of success is 0.80. So these are the parameters of the binomial distribution that X, the number of flights that are on time, has. Then the next question is, find and interpret the probability that exactly 11 flights are on time. This means probability, capital P, that X, the number of flights that are on time, is exactly 11. So in this case, what I need to do is go back to StatCrunch, and I'm going to set the appropriate parameters. Take note, in this question, our n is 17 and our p is 0.80. So I'm going to set that up, 17, n equals 0.1, n equals 17, and p equals 0.80. And I'm interested in the probability that x is equal to 11. Now hit the compute button. This is 0.06804. With that computation done, back to my working board, I would like to find and interpret the probability that fewer than 11 flights are on time. So what is fewer than 11 flights here? Probability that x is less than 11. So that will start from 10 rather, up to 0 or 0 to 10. In order to compute this, I'll go to StatCrunch again, and I'll change this to less than 11 in this case. And immediately the probability updates. If you like, you can check 0.0377. So at this point, we might observe that this is not just going to be just find, we're also supposed to interpret the probability. Well, to interpret the probability, we look at this example here. You will observe that this is about 6.8%. So 6.8% would mean 6.8 out of 100, or approximately 7 out of 100. So this interprets to mean that in 100 trials of this experiment, it is expected that about 7 will result in exactly 11 flights being on time. So to emphasize what was said earlier, and here it is on the screen, in 100 trials of this experiment, it is expected that about 7 will result in exactly 11 being on time. The 11 in this case, the 7 in this case, remember, we computed the probability of x equals 11 was 0.06804, which when multiplied by 100 gives you 6.8%. 6.8% means 6.8 or approximately 7 out of 100, since you can have 6.8 flights. So that is interpreted as in 100 trials of this experiment, it is expected that about 7 to result in exactly 11 of the flights being on time. A similar interpretation can be given to every other one here. So we'll focus on finding the probability, and we can use the same logic to interpret the probability we have computed. And that brings us to question E. We want to find the probability that at least 11 flights are on time. That will be X equal to 11, at least 11, or more than 11. So let's see how that goes. To solve this problem, I'll go to StatCrunch, and of course, I'm going to change this to greater than or equal to, and that stands at 0.9623. So here I've written that answer out here. Question F, we're to find and interpret the probability that between 9 and 11 flights inclusive are on time. What does this mean? Well, probability that between 9 and 11 using the less than symbol. But then something important to note, this says inclusive, which means we have to include the possibility that X is equal to 9 and the probability that X is equal to 11. So with that said, let me show you how to set this up in StatCrunch. You go to StatCrunch, there's a button here, click on between, and that will change the look of the interface. So we still have the same parameters, but this time it's starting from equal to 9 all the way to 11. Take note that these inequality symbols matches exactly what we have right here. So between 9 and 11. And so I'm going to hit the compute button. And so you can see that that takes care of that, which is a combined probability total of 0.1031. So I'm going to write that down. And here I have that probability. So how do we interpret this? Let's see. As it stands, this means that if I multiply 0.1031 by 100, I'll get approximately 10.31, which rounds down to a whole number of 10. So this means that in 100 trials of this experiment, it is expected that about 10 of these trials will result between 9 and 11 flights inclusive being on time. We now proceed to the next example or concept, and that is to find the mean and standard deviation of a binomial random variable. So, in a nutshell, once you isolate the parameters of the binomial distribution, namely the number of trials and the probability of success, it is a simple deal to get the mean and the standard deviation, because the mean of the binomial random variable is given by n multiplied by p, whereas the standard deviation represented by sigma for the binomial distribution is represented by the square root of n times p 1 minus p. Notice that the answer for the mean also features in the standard deviation. Now is a good time to take the first example to illustrate how to calculate the mean and standard deviation of a binomial experiment. In this question, we're told that according to the Gallup poll, 60% of our American adults prefer saving to spending. Let X be the number of American adults out of a random sample of 50 who prefer saving to spending. Calculate the average number of adult Americans who prefer saving to spending in this sample and the standard deviation. This is, first, we note that this experience or this experiment here is a binomial experiment where you have a fixed number of trials, 50, and the probability of success is 0.60. Then we would like to compute the mean. So the mean, which is represented by mu, is n times p. That will be 50 multiplied by 0.60, and that is equal to 30. Whereas the standard deviation represented by sigma is the square root of n times p times 1 minus p. So this would be the same as the square root of np we got earlier to be 30. So I can just sub that. So this is 30 times 1 minus p, which is 1 minus 0.60. What is 1 minus 0.60? That will be, on our calculator, 0.40. And this will be the square root of 12, which is approximately 3.46. And then we proceed to the next example. According to a recent Pew Research poll, 75% of American millennials, people born between 1981 and 1995, have a profile on a social networking site. Let X equals the number of American millennials that have a profile on a social networking site. Compute the mean and standard deviation of the random variable X that represents the number of American millennials that have a profile on a social media site based on a sample of 500 American millennials. This well describes a binomial experiment where X has the binomial distribution, N is the sample size, and P is the probability of success. So, to compute the mean and the standard deviation, the mean is N times P, and again, as we did in the previous example, we multiply N by P, and that gives 375, and the standard deviation is equal to the square root of N times P times 1 minus P. The answer for NP we had earlier, NP was 375, so I'm going to replace NP with 375, and 1 minus P, 0.75. 1 minus 0.75 is 0.25. So I can replace that. That'll be the square root of 375 times 0.25 is 93.75, and approximately the square root of 93.75 is 9.68. So with that done, that helps us to introduce the ideas of the mean and the standard deviation of a binomial random variable.